The microphone.
Okay. Okay, thank you very much. Good morning, everyone. We will start with the first keynote lecture, and I'm really happy that I can pronounce the next speakers. It will be two speakers. Christopher Newman is a Swiss pediatrician with the main interest in rehabilitation. He works in Lausanne University, and he's the vice president of the Swiss Academy of Childhood Disability. And Bernard Don is a pediatric neurologist and professor of neuroscience at the Université Libre de Bruxelles, the medical director of the Incendal Rehabilitation Center, and a member of the Royal Academy of Medicine of Belgium. He has a broad interest and he has a very keen eye for ethical questions. In addition, he's the editor of Developmental Medicine and Child Neurology. The speakers, they prepared their talk together, actually in French, but I will talk to you in English. And they will present on the theme of the keynote lecture, Big Data and Artificial Intelligence in Child Neurology. Please, the floor is yours. And they arranged their sitting so to have some kind of conversation. Thank you.
Thanks a lot, Jeroen. Try not to fall off. Hi, Bernard.
Hi. It's really good to be here.
It is, and we're going to have a great conversation.
You know how it started? So, can you hear me? Yeah. Jeannie Balick phoned me and said, "Oh, would you like to come to EACD?" Well, of course, I wanted to come to EACD. Would you talk about? And then I suggested either hypotonia or CP as a global health issue. And here we are.
And we're talking about something quite else, actually, which is big data and artificial intelligence. Maybe, yeah, just the...
Yes, we wanted to show this picture now to match my bow tie.
And my tie.
Really out of solidarity and sympathy for all the people suffering from the current war now and in the future. And I think that it's important to show our togetherness and be together, take action.
So maybe before we go ahead, what I'd like to do is actually hear a bit more from you. Could you launch that slide, please? So you just have to click on my screen, on the little white arrow. If not, what we can do now, let's do it with technology. Let's make this easy. We'll do it with hands up. Who uses artificial intelligence every day? Hands up. Well, a few of you. Okay. Do machines actually learn by themselves? Who believes machines can learn by themselves? Hands up. Small minority, actually. Interesting. And are machines objective? Oh, wow, that's a big failure. So no, machines are definitely not objective, seemingly.
Well, Tom thinks they are.
Does he?
You have a point, Tom.
So, more about that later on. And, well, this is a touchy one. Will AI eliminate certain jobs in the care of disabled children? Hands up for those who believe that. Well, again, more about that later on. You said Ginny got in touch with you to talk about this. Well, I actually was contacted by this guy called Paco. Paco, yeah. I got this weird message on the phone. Oh, there should be sound.
Hoe discovered your paper interstitial cells of cahalar normally distributed in a ganglionic bowel in sprungs disease with interest. We think this will be a great fit for our conference. We invite you to take part in EACD 2022 in Barcelona. Can you give a conference on big data and artificial intelligence in child rehabilitation? Thank you to contact me. Best regards, Paco.
So I'd actually heard about Paco a bit from Lourdes. She showed you the scientific committee earlier on, and we'd be discussing these keynotes, and she'd always say, well, I have to run this by Paco. I hadn't been thinking about him for a while, and then I got this invitation. I said, well, I have to look into actually who Paco is. And this is what I actually found out. Paco is actually an artificial intelligence who's set here in Barcelona and who basically organizes conferences. So this is why we're actually cast onto this meeting. It's an artificial intelligence who actually selected us, and that's why we're here talking.
Paco. Oh, that's good.
Next, well, could you just move it ahead a bit? Thanks. Yeah. Well,
I
that was a
think
bit too
we
fast.
see
Yeah, there you are.
trouble with physical intelligence.
Yeah, well, definitely we do.
Well, what is artificial intelligence? How would you define artificial
Well,
intelligence?
they're actually, I mean, it's a bit of a fuzzy definition, but what you find the most is that basically, and everyone agrees on that, it's all about computers and machines. So it is a branch of computer science. It's actually the intelligence of computers compared to human intelligence. And what it does is it enables machines to actually do things that we usually would do as humans, that is perceiving, generating and representing knowledge, generalization, reasoning, solving problems, learning, etc. You might have a slightly different view on that, actually.
Yeah, well, that's a book I read when I started to read in the early 1980s, but it's actually written in 1979. And in that book, Gödel, Escher, Bach, I learned about Zen Buddhism, about Bach, about programming. And then there was this sentence that stuck with me, is AI is whatever has not been done yet. And really, I think that this definition, so many years later, still exists. And so the first question, do you use AI every day? Yes, but many of us would not call it AI. AI is such a fancy word, but it covers also a number of disciplines. Can you take us through it?
Yeah, definitely. Well, artificial intelligence, actually, there's this thing that they call the AI effect, is that basically when the mystery of artificial intelligence disappears, then it isn't intelligence anymore. So typically, if you're on Netflix and you get recommendations, or even if you're looking on a search engine on the internet like Google, behind that there is artificial intelligence. And here on this slide, you can basically see how it declines between robotics, chatbots, etc. But what underlies a lot of it is actually mathematical tools. And that's what I've highlighted here with machine learning, deep learning, and neural networks. And these are basically the programming modules which allow artificial intelligence to function. So we're going to go a bit further into those modules. Sorry, I've lost it again. Next slide, please. Yeah. So artificial intelligence overall, and within that, these, I say, statistical and mathematical tools, which are machine learning and deep learning. So machine learning first. So there are statistical tools that are used to explore and to analyze data. This little additional picture gives you a bit more detail. There are basically two types of learning, what we call supervised learning, where basically humans decide on the classification. Typically, you'd have a picture of a field with sunflowers and poppies, for example, yellow sunflowers, red poppies, and humans say, well, the yellow ones are sunflowers, the red ones are poppies. They instruct that to the machine sees lots and lots of pictures and then learns to recognize those flowers. That's what we call classification. The other thing a machine can do is it can predict. It can use regression methods. And what it can do is, based on the number of sunflowers in the fields, it can then calculate the yield in terms of oil when finally the end of the summer comes. And what you can also do is that you can basically feed a lot of pictures into the machine and basically say there are two things in there, recognize them on your own. And that's what you call unsupervised learning. And behind these three methods, there are, well, different equations, different mathematical tools. You'll recognize some of them. Some of them have spooky names such as hidden Markov models. But it's basically all about mathematics. So what does this enable? This actually allows the machine to learn on its own. It allows the computer to draw inferences from patterns in data, which even us as humans might not be able to see. And Next, yeah, super. And basically what the machine and the computer likes is a lot of data. And that's why we call that big data. The more data is fed into the computer, the better it will get at recognizing patterns and increasing its performance in terms of algorithms. And that's why the term big data is there. It's basically you make those machines and those computers more performant by feeding more data into it.
Is there a definition for how big big data is?
There's actually not a threshold. If you actually look at the progression of the quantity of data in the world over the last 20 years, what you see is an exponential curve. And it becomes big data as soon as basically human organizations are not able to cope with the quantity of data. And actually, if you look at those curves, they are pretty impressive. To the stage at which actually people are now thinking about how to store the data, because it's becoming physically impossible to store all of it, taking into account the amount of data that we produce. Another tool that we do have is deep learning. So deep learning is all about what we call artificial neural networks, and ANNs are basically mimicking animal neural networks to be able to process data, especially several streams of data, and from that to then get an output. It's actually mathematically very complicated. It's impossible to actually understand even what goes on in what we call the hidden layers of those networks. Therefore, there's this black box effect, and that creates a big element of trust or untrust vis-a-vis of these machines. So now that we've basically talked a bit about artificial intelligence, should we talk about how it could apply to child rehabilitation?
Yes, but before we do that, let's try and remember how we used to look at children with disability. So if you can remember as early as earlier this week, what did you do? You probably looked at situations. These situations were very complex, and you had very basic technology. So sometimes you use tools. It can be a jerk hammer, it can be a puppet. You look, and then you try and identify within this complexity patterns that you recognize and that relate to your experience. And then you try to make a diagnosis based not on the full picture, but on things that you extracted, combined with your experience, your knowledge, and your recent experience. So you're more likely to make a diagnosis if you've seen something similar recently, even if it's rare, might not be right. And then your exercise is to say what it is, draw the future of the situation, and perhaps suggest some clues to management. You use internal algorithms, and is that how we will be doing with artificial intelligence?
Well, it might be. Let's try to imagine what the future could look like. So let's take the same child, but we'll take him earlier on. He's just born, and well, the parents are lucky because basically they're within this big health team called Alphabet Global Health Ventures, and they get this complimentary neonatal follow-up, which mixes up, brain MRI, live monitoring via biometric cameras when the child is within the neonatal unit. There has been a bit of also tracking and follow-up of the mother's pregnancy, and of course he gets also a whole genome screening. And based on all of this information, which is fed into this artificial intelligence called Holmes comes up with, well, sadly, with this prediction, which is that the child has a 99.12% risk of developing cerebral palsy. Well, what happens next? Well, the child gets transferred over to the sub-company of Alphabet, which is called Fuful. And Fuful is actually going to provide care for this child as he grows up. So, of course, there are physicians in Fuful. And what is the care actually going to consist of? Early intervention, of course. The child has been diagnosed very early on. So very early on, his care will start. He's going to continue to be monitored throughout his lifetime with, again, biometric cameras, with sensors. And this data is going to be continuously fed into Holmes, the same artificial intelligence, via satellite links, via 5G. And what the physician's role is within this model is that he is going to set with the child and his parents objectives in terms of determining the optimal level of fitness, of participation, of happiness. Again, this is going to be fed into the mainframe computer, and from that there's going to be a care plan, which we'll call Optima, personalized care plan. Now, what happens next? This child is going to go into this great place called Fit and Fun, which is basically where you care for children with child disabilities in the future. He continues to be continuously monitored with sensors, and there's this person, the CTO, the Chief Therapeutic Officer, who's going to basically direct how this child is cared for, helped by a small army of social robots who are there to motivate the child. Actually, the child gets his own robot who follows him around and allows you to get home care programs as well. And of course, all the latest technology, exoskeletal support for walking, virtual reality. So I guess this is kind of how we could imagine the future.
Yeah, well, that's a very near future, because I see the early intervention starts at birth. Not prior to birth?
It actually could, now that you say so. Probably based on the genome screening, certainly we could start even earlier. The thing is, well, I mean, it looks a bit weird and strange and sci-fi like that, but what we actually put in there are either projects that already exist or projects that are currently being developed. Well, not all together, but putting these building blocks one with another, you actually are able to build that type of scenario for maybe not the so far future.
Well, and actually we've got those robots at the hospital. So one of the things that you started with and I started with is this observation and what you make of complex situations. And I said that we very much being influenced by our recent experience and our knowledge. And there's been this important study published in 2015 by people from UC Davis. And they took the problem of pattern recognition. And one area in medicine where it's very obvious is looking at pathology. So they said, would pigeons be able to recognize, to be trained to recognize malignancy as opposed to benign presentations? And actually, I don't know if we have the videos, but what they did is they took 16 pigeons and they taught them to recognize feeding them when they had it right, and they reach 85% of success, which is really not bad from a pigeon, for a pigeon, but it's not enough for us. And then what they did is they took all the flock and they took the responses that most pigeons had chosen, and they got to over 99% of right replies, which is very good, and it's actually better than what we would do. And so that was very interesting. And then the question becomes, well, if pigeons can do it, can we train machines to do it? And of course, we can move further.
So you're saying histopathologists are actually less intelligent than pigeons?
According to your definition of intelligence, yes, but I'm not sure I would let, well, a pigeon decide, and a pigeon can learn based on what we show them, but they can't be very creative, and sometimes clinicians need to be creative.
Definitely.
We have this example. So there was a team then, Ribeiro, who the following year, and unrelated to this specific research, said, well, how would we trust machines? How would we trust an algorithm? And do you want to take us to their experiment?
Yeah, definitely. Well, there's a picture behind this. What I'd like you to try to do is basically imagine the picture. And this is what, when the computer, which is basically, we talked about deep neural networks earlier on, and this is Google's most performant deep neural network. What I'm going to show you is what the computer understood, and try to understand on your side. So this is basically, and this is how computers work. They're going to identify what they call hotspots, or regions of interest within a picture, and they're going to basically match that with their own personal database of knowledge. And so this is basically the first explanation. You saw the picture, and this is probably an electric guitar. You might agree with him. Ah, well, is this really an electric guitar? You can see what the guitar actually looks like, and the computer isn't too bad. It actually is an acoustic guitar. And well, what's this doing here? Yeah, I agree. It certainly is a Labrador. So try to figure out what the whole picture could be. A few seconds for that.
And so this picture really exists. I mean, this is a picture from a scene. It's unusual, and you saw what the computer made of it, what the clinician made of it, but it highlights the possibility of biases, because we try to identify patterns using some rules, simplification rules, and so we select unconsciously or according to ways that are not quite known and possible to follow within the dynamic neural networks, some aspects from which we extract patterns, and we might just get it wrong. So one story that people like to tell, and I'm going to share it with you, is that experiment of artificial intelligence fed images of wolves and huskies, and asking the neural network to learn the difference. And the neural network was excellent, excellent. So good, 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 good. Perfect coherence until sometimes it wasn't good. And here we see that on the bottom, you see predicted husky, but it's a wolf, or predicted wolf, it was a husky. The real question we have to pose is, how did the computer do it? How did you recognize it? You probably don't know how the computer did it. And here, the analysis of what the computer used to recognize in a snap whether it was a husky or a wolf was actually not the pattern of the husky or of the wolf, but the presence of what the computer identified as being snow. And this is one of the mistakes. You see a husky classified as a wolf, and the salient elements that the network used was these things that appeared to the computer as being snow. Of course, we do that in clinic, and it's good to know that we do it. And so the question becomes, how does it work? What can you expect from computers? And what can computers give us? And there was this interesting study you found.
Yeah, actually, if you think about it, well, we have seen basically computers can make mistakes, but the other thing that they can do is that they can process vast amounts of data and beyond what we can actually do with our visual system and basically with our brain processing capacities. So this is an interesting study from last year, basically, where the team were able to predict autism based on neuroimaging and then putting it into machine learning algorithms. So what they put together was basically a mix of resting state fMRI and of structural MRI features, which basically gives them combined models with connectivity among it. And once they fed that into different algorithms, and this is what you see on this basically complex figure, what you have at the top are the features, again, the feature sets that the machine was looking into, and what you have along the vertical axis is the type of algorithm that the computer was using. And when you go further down, basically you're going deeper and deeper into what a computer can do, you get into those green little squares, and what you can see is that best models with the best images are actually able to predict autism at around 80%, which is probably better than at least what I could do.
And certainly based on imaging.
And certainly based on imaging. Again, I mean, if you look at those images as humans, you will see nothing. And so this is basically, I'd say, a demonstration of, yeah, the power of machines in helping us in diagnosis and prognostication. Would you agree with that?
Well, I think it's a very interesting study, not so much in the results as in the questions. So you say helping us in diagnosis autism, but one of the questions I have here is then, is the autism category a valid one? If we're going to approach it through technology, and you say connectivity is a construct. So they do not access connectivity. They construct connectivity based on imaging sources. And autism is certainly also possibly the best we can do for this condition for the moment. But perhaps the presence of this kind of tools calls for other categorizations. The other question is the question of prediction. And this is an example from epilepsy. So for a long time, we have been looking at EEGs at what was preceding a seizure, and we called it pre-ictal state. And that was with a deterministic view that, knowing that there was a seizure, we went backwards just before the seizure and saying, oh, we have all the elements there that are really the seizure starting. So I remember looking at EEGs and EEGs. I showed this, it was paper at the time, and looking at the little feather of fast activities. It's, yes, this is the pre-ictal state. It doesn't work. It hasn't worked. And now the idea is perhaps we shouldn't be so deterministic, but look for pro-ictal states, and thus conditions that put you in a statistical likelihood statistical constraints like weather forecasting. And I think that we can approach much of what we do in predicting children being at risk with pro rather than pre-conditions. Yes, this is another question we had.
Absolutely, about precision medicine, because yeah, basically I mean, it's talked about a lot at the moment. That is that based on all of this data that you're feed into the computer, and again the diagnostic elements, the prognostic elements that come out of it, you will be able to adapt your treatment as best to offer basically individual medicine. So does precision medicine actually mean that there are going to be 7 to 8 billion different types of medicine throughout the world?
Well, this is not really what people involved in individualized medicine are trying to achieve. What they're trying to do is actually make groups. And so not to have so many different groups, but not the same groups as those we use now. To have a restricted number of groups, and then classify everyone, constrain, push them into a category. Now, when we look at the literature involved in precision medicine or individualized medicine, it's really interesting to see where those papers come from. And you see that there's a lot of concentration in Western Europe, in North America, some other places, and what they call big data. I asked you the question, they ask the papers the same question, and it can be very, very variable. What's also interesting is what people now think that precision medicine is about. What would you say? What would be the salient thing? You showed us imaging.
Well, it's all around imaging, I mean, diagnosing, prognostication, but then there's
genetics?
Well, genetics certainly would play a role in that.
But there's very little beyond genetics and imaging. There's also very little beyond body samples. And very interestingly, there's a small minority of studies engaging people. And so I'm not sure that, well, the approach might be right, but the way we've been using it might not provide answers to our current thinking and what we think should be our thinking for the near future, at least.
One of the things that can certainly help and add to that is what we call dynamic monitoring. Well, people also call it the quantified self. That is, of course, we have all of these neurobiological aspects, but probably that there are also biomarkers that we have via our activity. It can be maybe considered a bit reductionist as a view, saying that we're basically just a set of numbers, but that's what computers ultimately do. I mean, they do create sets of numbers.
Yeah, my worry is that it tends to replace you by those numbers. You know, all those people counting their steps in the day, is that their day? I mean, I say that because I can't use a machine. But the other thing is, I think that if you're constantly monitoring, is that necessary? Do you really get a better picture? What do you say are the advantages of continuous monitoring?
Definitely what you do get on top as a clinician is that you will get a view of what the child is actually doing in his real life. That is, I mean, you saw that picture earlier on where you had that clinical observation, but all that happens within the clinic and does not reflect what really goes on in real life. And one of the big advantages of dynamic monitoring, which you can do via wearables, which are basically measuring constantly acceleration, is that you are able, from raw signals which are completely illegible, and again, this has to be processed by a computer, you can get to activity detection. When is the child actually being active? And again, using computer intelligence, then you're going to be able to recognize what activities the child is doing at what moment of the day. And of course, this is, there is the subjective experience, but we do know that what children and their parents do tell us does not at least perfectly reflect what is going on in daily life. And this actually works pretty well. There are now quite a big series of statistical machine learning studies that have looked into that question and who are able to classify different types of activities: walking, lower limb, wheelchair use, upper limb. And this is a body of literature which is building up constantly. That's a systematic review from 2020. It's actually a second page like that. And definitely if we had to review that literature again today, probably this literature would have doubled or tripled.
So I guess one advantage is that it's more objective than if you were using questionnaires, and you don't need, well, the engagement, the cognitive engagement, is saying, well, this, I am identifying this as activity. But it's quite gross, really. I mean, I suppose there's a trade-off between artifacts and for activity, it works well. But if you want EEGs, well, of course, there is a lot of work on EEGs. And I suppose there is a compromise to find.
There's a compromise to find, and you have to realize that basically the devices are becoming smaller and smaller. The computers are becoming more and more powerful. So these wearables are easier and easier to use. So I do believe that over the next 5 to 10 years, as we have seen over the last 10 years, there's going to be a big change in paradigm, and the use of these devices, which are also going to become much cheaper, might become more generalized within our community.
Do you think they will replace hospital-based equipment?
Well, that's actually a good question. There are actually already a couple of models out there that basically look into the meta-organization of how rehabilitation could be done using this type of device. And here you have an example of a recent study where putting together a different number of robotic devices which are available either within the clinic or at home, and basically transferring data from the clinic to the home and from the home to the clinic and processing it via an artificial intelligence, you are able to basically have, we've talked about personalized management in medicine. Well, basically, this is a personalized management plan based on the feedback and feed-forward in data between the user and between the medical professionals. And as I said earlier on, that the scenario that we discussed together is not completely fictional. I mean, these are things that are actually being conceptualized and put into application at the moment.
Well, people have certainly proved their case in other disciplines, say in cardiology, in intensive care, but probably their decision algorithm is based on harder data than what we currently have in rehabilitation?
Harder data and lots of data. That is, not only do these computers skim the literature for basically human knowledge, but they use the knowledge that they constantly build up based on the feedback from basically users to, well, I'd say increasingly improve their algorithms. Now, we mustn't be too optimistic about this either. I mean, it's far from perfect. I mean, there are issues which are logistic issues. There are issues with the algorithms. They're not always, far from that, good at what they do. But that's basically this, I'd say, strong trend. And, yeah, but, well, should we actually, do you think we should be scared of the machine?
Well, we make the machines, we use the machines. I think we should be scared of ourselves in the way we use the machine, but not of the machines. Transformative, yes. I think that we have been experiencing this transformation. And what it has been transforming is the relationship we have with machine. And I don't think it's either man or machine, really. It is new questions that can be posed. But we have to follow the same values and remain child-centered, family-centered.
Oop. Sorry, I went too fast.
The question is, how do we manage the added value, which is clearly the human expertise, human experience?
Yeah, definitely. I mean, what we've shown here are what we call limited artificial intelligences. That is, I mean, there's this good example of the computer that beat Kasparov at playing chess. If you'd got him to play, I'd say, bridge or poker, he would have lost. I mean, all of these AIs are very much task-focused, and for the moment where we are not replaceable is in the general intelligent aspect. Things like common sense. A computer doesn't have any common sense. So definitely our expertise and experience are necessary to build up these partnerships and to make them efficient.
At several stages. I mean, from conception, some form of supervision, and certainly interpretation of data, as we have been seeing with genetics, for example, well in our daily practice. And then we thought of equity, which is so important. I mean, this enhances the possibility of differences, of social differences, economic differences, and we really need to think of access. And it is not because it's based on a high technology that it is to be equated with expensive technology or with limited access. Sometimes it enables access in places where you wouldn't think you would get it. And this is an important thing to keep in mind. Let us not divide the world even further than it is being now.
Well, of course, one of the issues is around protection. I mean, the machines are not there to basically dominate us, but they're here to help us. And we have to be clear about that, there are issues about data protection, about the integrity of people as well, psychological, physical integrity, and definitely also our freedom of will. I mean, we talk about decision-making, but the decisions ultimately should rest in the hand of humans and not in the brains of machines.
You know, our time is up.
Disabled children are not machines to be repaired.
What did Paco say? Oh, disabled children are not machines to be repaired. Oh, thanks, Paco. I didn't understand you. But yeah, so we'll leave you on basically Paco's very wise words, and I think that's it for us.
Yeah, I think that we have two questions. I thank you for this, yes, on behalf of the public, of this very nice presentation. We have time for one or two questions. And is there someone with a question? Yeah, over there. Dr. Hollers.
Yeah, thank you very much, Christophe and Bernard, for your very nice presentation. Christophe, you stressed big data, big is better. But I would stress, wouldn't be the quality of the data of very much importance? Otherwise, you would classify a dandelion as a sunflower, I'm afraid.
Absolutely, you're completely right. The issue of quality of data is paramount in artificial intelligence. And actually, machines for the moment are pretty bad at basically cleaning data, and that rests on humans. There's actually, even if you look onto it in Amazon, Amazon has this module which they call the Avatar Turk, basically. This is an old story. In the 19th century, there was this false Muppet which looked like a Turk and who was able basically to compose music. And what they'd actually discovered is that there's a human hiding behind it. And what they do via this service is they have people working in lower resource countries who actually take in big data sets and who clean them up. So machines for the moment are not good at making good data. And for that as well, we do, at least for the moment, still need humans.
At all stages. So they need to be clean to start with, and then a lot of maintenance. Mm-hmm.
Yeah, I think there is was one more question in the back.
Hello, thanks for your talk. I'm working for Massive Ionics, which is a company that has developed the first portable exoskeleton for children that cannot walk. And I'm wondering how big data can help exoskeleton technology to improve this technology. I mean, I think it's very important, the connectivity between different technologies to make them better. Thank you.
Well, certainly to make it fit for purpose. And I think that's a key thing. So you may make a reduction of locomotion as just a displacement. But if it is really to be used and to be useful, it has to be locomotion for a purpose and also in a way. And I'm sure that big data, in addition to the right questions, will also include a lot of patterns which we don't take into account if we have to tell about it. And for example, kinematic aspects like jerk, so further than acceleration, that would be related to smoothness and graceful movement. Perhaps that's the end of what I can say.
Okay, and thank you for this very nice, smooth answer. First of all, there's the slide on the RIA Tech survey, and we please ask, because of the EACD, to scan this and do this survey. It's really important that we get some big data about this tech involvement in childhood rehabilitation. The other remark is that we have a shorter coffee break, and we ask everyone to start a new session at 10:30. So, and thank you very much for a wonderful presentation.
Thank you.